Okay, so we are currently within, these two numbers are within 0.5%, which is pretty good, but we can do better, right? So our initial assumption, the nucleus doesn't move. Now, while it might not seem that that's the simplified version, we can add in the nucleus moving, right? Which adds another layer of complication, but it gives us a bit more accuracy. So if we look back, where did it go? No, I guess this is where I was going to drive it. This sort of expression here, right? We're going to use this idea, and I'll redraw it so that I can get my board back. If we have two masses revolving around each other, sort of like a binary star situation, where one of them is a lot more massive than the other, there's actually a location in between that they're going to be revolving around. Right? So if this is mass 1, and we'll say mass 1 is more massive than mass number 2. And in our example, that would be the nucleus, that would be the electron. Right? I'm going to use this distance here will be R1. That distance there will be R2. All right, and then the total distance would be R. This was the same R that we already worked out. Right, the radius, the distance between the two. But what we're going to take into account is instead of having the small mass going around, we're going to use what's called the reduced mass, which takes into account both of them moving. Right, so we're going to complicate things a little bit by allowing the nucleus to move. What it means is we have to figure out the effect that that's going to have. Okay, so if the two are revolving around each other, you can think of it as having sort of two fulcrums, or two forces moving. And so what that means is that the mass of one times its radius is going to equal the mass of the other times its radius. All right, the lower mass is going to be moving at a further distance, the higher mass is going to be moving at a shorter distance. Okay, and we're going to also use R is equal to R1 plus R2. So we can express R in terms of everything else, and we can, we can express R1 in terms of just the masses. So if we solve the top equation for R1, we get R1 is equal to M2 R2 over M1 and we can do the same thing for R2. R2 would then be M1 R1 over M2. Plugging these both back up in here, right? Oh, yeah, gets me R is equal to M2 M1 R2 plus R2. If we take this as being replace this with M1 over M1. Doing cross multiplication to bring them, bringing them together, this would be M2 plus M1 over M1 times R2 is equal to R itself. Rearranging that to solve for their R2. R2 would be equal to M1 over M2 plus M1. Or, to be consistent with what I actually have in my notes, M1 plus M2. You look confused.
I'm a little lost in the steps from the bottom, fourth and the third. So like R equals M2, R1.
This one?
Yeah.
Okay. So, taking this, solving for R1 gets us this. I can take this and plug it into here, giving me this one, right? Now, I got R2 in common, so I can pull the R2 out, giving me M2 over M1 plus 1, but I want to be able to add them together, so the value over itself is equal to 1. So I do that, I can now bring them together, giving me this. You good there?
Yep.
Okay. And then solving for R2 would be moving this to the other side or multiplying by the reciprocal, giving me that. I can do the exact same thing, set of processes for R1, and that would give me R1 is equal to M2 over M1 plus M2. Okay, same process, it's just instead of here instead of here solving for plugging R1 in, you plug R2 in, you'd end up with the same process. Okay?
So when you solve for R2 and R1, doesn't the R on the left still stay the bottom?
Oh. It does. Okay. Whew. Gotta be more careful.
You don't have to like. I'm totally.
That's fine. It's fine.
Let's have a limit, like an after like 5. It's like okay, whatever.
Okay. We'll come up with a limit. You can share some of the insight with your neighbors.
Sure.
Okay. So we got this. Our kinetic energy, right, would then be how fast both things are moving. Right? So our energy kinetic is equal to 1/2 mass of 1, velocity of 1 squared, plus 1/2 the mass of 2, velocity of the second one squared. Okay, now because we're talking about two things rotating and not moving in a straight line, we're going to be talking about the angular movement. And so V1 would actually be the radius times the angular velocity, the radius of 1, and then V2 would be the radius of 2 times our angular velocity. Now, because both of them are moving the same number of radians per unit time, they both have the same angular velocity. Okay, so this is the same for both. So plugging this back up into there, we get energy kinetic is equal to 1/2 m1 r1 squared plus 1/2 m2 r2 squared. You see that we have both the 1/2 and our angular velocity on both of them. So we can pull that out. Energy kinetic is equal to 1/2 m1 r1 squared plus m2 r2 squared omega 2. Now we have expressions for R1 and R2. We're going to plug the ones that we came up with before up there. Energy kinetic is 1/2. So this would be m1 times our value for R1, which would be m2 over m1 plus m2 squared. What's in the parentheses is R1 that we came up with before.
The R still
Well, yeah, we'll get the R in. Do I want to do this? Yeah, I'll do it in 2 steps. So, times R plus M2 M1 over M1 plus M2 squared R, just this, omega squared. I got R on both of them. R squared and R squared. Just pulled it out. You okay or no?
No, it's fine.
You good?
Yeah.
Okay. We can do I, which is equal m1 r1 squared plus m2 r2 squared. So essentially this whole thing here is our moment of inertia. What's within the parentheses is a moment of inertia. Okay. Now we can simplify, so we can pull the R out. So this would be energy kinetic is equal to, remember from before, 1/2 I omega squared. So this is equal to 1/2. We can simplify this. This gives us m1, m2 squared. I'm going to keep what's in the bottom within a set of parentheses. Okay, and we had R on both of them, so I'm going to pull the R. Oh, sorry, I had R squared on both, so I can put the R squared out here. Omega squared. Okay, so this part here, let's see. We can write this as we pull out an M1, we get M1 plus M2 times, sorry. We can then also pull out an M2. So that would give us yep. There we go. This is divided by M1 plus M2 squared. And so what's inside the parentheses here, so we'll cancel out that. So this gives us energy kinetic is equal to 1/2 M1 times M2 over M1 plus M2 R squared omega squared. Did I do too much hand waving there?
I was like catching up. What does that?
This step here. Anybody go over that again? No? You got it? Okay. So this term here inside the set of parentheses, this is a very specific value. This is called the reduced mass. It gets a symbol of a mu. Right? It ends up getting used a fair amount. So it's called the reduced mass. You can see if you compare it to, I think something that I already erased, right? Instead of using the mass of the electron, we use this value. So if you go back through your notes, you can see that our here, at some point, we have the mass of the electron alone. The value here, if you work this out, plugging in mass of the proton, but if we're talking about a straight hydrogen atom, not deuterium, this would be the mass of a proton, mass of an electron, so the product of the two divided by the sum of the two. That ends up being equal to 9.1048 times 10 to the negative 31st kilograms. If you compare that to the mass of an electron here, it's similar but slightly smaller. This is essentially equal to 0.9995 times the mass of an electron. Essentially, the reduced mass is 99.95% of the mass of an electron. Right? Not a huge difference, but if we use the reduced mass instead of the mass of an electron, that takes into account the fact that the nucleus is actually moving. The value that we get our new Rydberg value is equal to 1.09676 times 10 to the negative, times 10 to the 7th. Times 10 to the 7th meters minus 1. Right, so before we had a difference creeping into the, what, 4th? Yeah, essentially the 4th decimal place. Or I guess, yeah, about the 4th. Right? Here, it's the 1, 2, 3, 4, 5th decimal place now that it varies. So it brought it closer together, but there's a decent amount more work involved in getting that little bit of extra accuracy. Right, so including the fact that, or removing the assumption that the nucleus doesn't move, gets us an even closer value to the Rydberg constant. So what that tells us is that we're on to something when we're using Bohr's model. Or at least Bohr was on to something for his particular model. A little bit better than the previous one. You good with all that? Yeah?
So,
Yeah, essentially what I'm trying to get at is if we remove assumptions, we have to do more math, but we get a better number. With all of this, the question is, what's the appropriate amount of laziness you should have? How accurate do you need the number? If that's accurate enough, there's no point in going through the extra effort. But if you need it to be very accurate, start pulling assumptions which will make the math more complicated, but it will give you a more accurate answer. Okay? Okay. You guys got all of this? Okay. Okay, so we're actually going to do a calculation that's similar to the homework. So the homework got posted. Hopefully you guys both got the email. Yes? Okay. So it is due on I believe the 19th. It actually says on it. And then questions from memory 4 and 7, but it says on the homework. Those are going to be the two that get graded. And I believe it's either question 4 or question 7 that has multiple parts, right? So it's all of question 4 and all of question 7. You got to show your work, okay? The other ones are there to do for practice, but they're not going to be graded. They are an excellent idea to do them because it's stuff that'll be similar to what you might see on an exam. Although I think question 1 wouldn't, because you actually have to use numeric methods, which is why it says use Excel. So you won't have access to Excel on the exam. Okay, so determine the wavelength of a baseball thrown at 92.5 miles per hour. A couple of useful values. Baseball weighs about 0.1-ish or 145 grams, about 0.1 kilograms. And there's the speed. So that is I think that's sort of major league-ish speed for a fastball, 92 miles per hour. It's pretty quick. So, what's the wavelength of the baseball? This is for you guys to work out.